Okay, so we have looked at how position goes to velocity and the relationship between position and velocity, and how we take a position graph and go into a velocity graph. Well, we can also look at how velocity is related to acceleration. So this mini lecture is going to look at the velocity and acceleration relationships. We're going to talk about it both mathematically and graphically like we did before. So what we want to make sure that we remember is what acceleration is. Acceleration is the change in velocity as time goes on, so through the time of our motion. And if we talk about it in the same terms we talked about it with position and velocity, it's the rate of change of the velocity. So the acceleration is the rate of change of velocity. And if we remember the equation that we used to describe acceleration, we said that the average acceleration was the change in velocity over the time of the motion that we care about, those chunks of time, which we've now also shown as that change in time. So change in velocity over change in time. This looked very familiar to our change in position over change in time. This relationship represents a general rate of change or a slope. So the slope of the velocity versus time graph is equal to the acceleration. Just like the slope of the position versus time graph gave us the velocity. The rate of change of position is velocity. The rate of change of velocity is acceleration. And similarly, if we take instantaneous acceleration, we find that the acceleration, just like we did before, is equal to the derivative of the velocity as a function of time. Now, we're only going to look at constant acceleration through this entire course. So the derivative and our discrete change in velocity over change in time will always be the same because we are only looking at constant velocity, constant acceleration. But in a generic sense, in a true physical representation, the acceleration is in fact the derivative of the velocity as a function of time. And just to make our calculus full circle, we want to remember that the velocity is a derivative of the position with time. Okay? So that tells us that the acceleration is the second derivative of position. All right? So acceleration is our second derivative of position. So does that work graphically? Well, it needs to, right? Because that is, in fact, the slope. Acceleration is the slope of the velocity versus time graph. So let's see if we can talk about what the object is doing in terms of acceleration by looking at the velocity versus time graph, and then use this idea of slope to represent that in the acceleration versus time graph, and we should see that that's consistent. So in this velocity versus time graph, and this is a good review of how to read these graphs, we are positive. We are moving in the rightward direction. We're above the axes. And the line is horizontal. It's at a steady rate. Well, the rate of change, the slope of this is 0. Does that make sense? Well, if the velocity is steady, if it's not changing, the acceleration is 0. So it should make sense. And it does. So our slope represents the acceleration during that time period. Okay, what about during this next time period? Well, my velocity is decreasing, and then it starts to turn around and starts to increase. So that was our interpretation of the velocity graph. The slope of this is negative. So let's look at the first part. So the acceleration then, if the slope is negative, the acceleration should be negative. So is it negative during this first half? Well, our velocity is positive. We're moving to the right and we're slowing down. Moving to the right, slowing down, velocity and acceleration should be opposite. If velocity is positive, acceleration should be negative. Good. And what about in this part of that time point? Well, we're moving to the left. I'm below the axis and I'm speeding up. If I'm speeding up, velocity and acceleration are the same. Velocity is negative, acceleration should be negative. So during this whole time period, the acceleration is negative. During this whole time period, the slope is negative. So again, they're consistent. So we are at a negative acceleration. Right now we're at this point in time and the velocity is moving to the left, but at a constant rate. The acceleration is 0. The velocity is not changing and the slope is 0. And then as we look in this situation, we're still moving to the left, and we are getting slower and slower and slower. If we're moving to the left, negative, and we're slowing down, the acceleration and the velocity have to be opposite. The acceleration should be positive. The slope of our velocity time graph is positive, and so that is consistent. And this might be a little shallower, so I'll make it a little less of an acceleration than my negative acceleration. Great, and then the last time point, of course, we are at 0 velocity. We're staying at 0 velocity, so we are not changing our motion at all. So our acceleration graph from this velocity time graph, if I accept and understand that the acceleration is the rate of change of velocity, which is the slope of the graph, we can go from a velocity graph to an acceleration graph. Mathematically, just as a reminder, just like it was for between position and velocity, our rate of change is our discrete rate of change, and that turns into our derivative as we make those time points smaller and smaller. So our acceleration is the derivative of the velocity function, of the velocity relationship, and since the velocity is the derivative of the position relationship, our acceleration is the second derivative of the position relationship. All right, good job.